Good afternoon, everybody. Thank you so much for the invitation. I am here to show you recent work that we've been doing as part of a project funded by the Department of Energy and specifically the Office of Advanced Computing on using simulations like the ones you've been seeing all day to do applications, development applications of machine learning. The people who have contributed to the work are shown here on the front. And there's more coming. So thank you, John, for setting up my talk earlier today. So imagine a distributed infrastructure system. And if we want to reliably estimate the risk of such a system in an ideal world, we will want all those scenarios that John was running before, all 95 of them, to be accurately represented by ground motion simulations and have specifically the time series at every single point so that we have the spatial correlation at the highest resolution that we could have at all the spatial scales that matter, be that a specific structure or a specific I don't know, a piece of infrastructure, then all the spatial correlations, the connections between the different components of the system. The short period for the buildings and the shorter period for the instruments, but also the longer period for the pipelines, etc., and even longer period for the cables. Now I'm going to apologize profusely because I am sharing the wrong presentation. Isn't that amazing, right? Isn't that? It starts, however, very similarly. So here I go. Excellent. See? So basically that's it, but then the tell-all was that the next slide was not relevant here. So now the exascale, the exascale computing project of the Department of Energy, as well as the variants thereof, among others the AQSIM and peer collaborations with peer, have made possible simulations like the one we've seen all day. So extremely high resolution realizations of large magnitude events on the Hayward fault, and have created the opportunity for us to actually be able to realize this dream of having very high resolution, multi-scale spatial correlation of those ground motions. But the output of those simulations is as accurate as the input, right? So the geology, we know as much as we can, and there are certain things, you call it the geotechnical layer, and I'm a geotechnical engineer, and I tell you, I don't like it. Let's call it the path near the surface, right? With the three-dimensional components that reach the surface. We don't know it as well. Geotechnical engineers don't know it as well. And then the rheology, and the hydrology, and that's everywhere, and on a spatial scale, on a regional scale. We don't know at the detail that we would like to know it. So there's one. So I'm not saying that that's bad, I'm just saying that that's uncertain. And so I would like to have many realizations of those simulations, right? To be able to capture that epistemic uncertainty that I don't know. And then the second is that the computational cost of those physics-based simulations, the perturbations thereof that I would like to include in order to get the risk assessment of those distributed systems to sample the full distribution of the hazard curve would be enormous. Right? I don't have only one scenario and the variance of the moving of the hypocenter. I have a whole bunch of other faults in the region that describe the hazard of the allocation and so on and so forth. Smaller events and that happen more frequently, etc. Right. So now imagine that distributed system is in the San Francisco Bay Area. And so you sample the scenarios of the hazard given allocation, and you find it's not only Hayward's fault, this fault. There's other things that contribute to the hazard. And now you want to add, and you don't have those simulations in hand, right? And you want to, on top of that, include the uncertainty, so the things we don't know, the geotechnical layer, which I said I don't like, and then I use it, which defeats the purpose of my preaching anyway, the source, the hypocenter, the velocity model, etc. So what do? The first option is you go back to the Macallan and you say, run another that many scenarios. Or you go to your personal supercomputer. And the other option that we came up with was to develop a hybrid simulator. A machine that we use the simulations to learn how waves propagate in the San Francisco Bay Area, so that then I can choose a different location, a different fault, a different site, and say, I want an earthquake here. And then the waves can propagate in that velocity model, and hopefully in the near future, end perturbations of the velocity model thereof, and get the results in a few seconds on your personal computer. With all the mistakes that models entail, right? So I'm not saying throw the observations away. I'm going to tell you how I'm going to plan to put those back inside. But for now, that's the idea, right? So the cool thing about, and the problem at the same time with the Office of Advanced Science Computing is that we needed to demonstrate we also made fundamental advancements in the computing side. We could not take computer science off the shelf and say we machine learn using this algorithm. So the way we did this is we used the fundamental basis. I'm using here a visualization that I thought was cool. But assume as a fundamental basis, you have an unknown distribution of a bunch of data in this location here, and Caltech 1. Right? These are observations or some simulations. You don't know that distribution, but you would like to learn it, and you would like to learn the distribution from a sparse set of observations, such that when you sample that distribution, you get observations that look like the observations that you have. They're not going to be identical. This is a probabilistic problem, and this is what we call a generative algorithm, right? It creates new content. Because you want new earthquakes, you want new scenarios, you don't want to replicate what you have. We're not doing interpolation, correct? So, and in fact, what you want to do is you want to be able to replicate this unknown distribution, where is my mouse? Somewhere, from a simpler distribution here, which is here a Gaussian. In the flow matching community, which is a generative model paradigm that's getting a lot of attention in the recent years, see ChatGPT and generation of pictures and videos and blah, blah, blah. This connection between the known Gaussian and the unknown distribution is done by neural networks, right? Slowly, slowly, slowly go from a known to an unknown. What we developed is what we call an operator flow matching, which is a continuous function, a functional, our infinite space connection between the Gaussian process and the target stochastic process. And what that allowed us to do was to create a resolution invariant connection. That means that I can sample distribution on the right at, let's say, 1 hertz, and I can produce a super resolution at 5 hertz. Right? And that was great because I had a lot of data to learn. It was not easy. So that was the advancement of the computer science. I mean, it's as simple, and if you ask the computer science, they will say, I don't know what I'm talking about, but that's as much as I understand to explain. So we built a mapping from the Gaussian process on the left, which is an easy thing to do, to the right. Not only is continuous, but it's also invertible. We can go back. Right? And every time we sample, we generate new content that looks like the previous one. So the problem was, again, that the data that we had was really, really big. There's several people explain how big those ground motion simulations are and the amount of data that we had. So it was not enough for us to generate a continuous functional space. It was easy to do that for relatively small problems for wave propagation, for 3 components. But it was hard to do that for the entire Bay Area. So we needed to do 2 things. First was a way to translate the big problem into small problems. That is called a latent space. So basically, take a complicated problem and make it to something small that you can then learn, but then be able to go back to the complicated problem. So we developed this transformation here, and that gave rise to what we call the latent operator flow matching. This was enough for us to learn the following problem. For example, what I call real data here, and I apologize to the gentleman in the back who keeps saying that real data is not simulations. I call real data the data I want to learn, right? On the left-hand side is a random field where I have a point source somewhere in the middle, wherever is not is a conditional on the location of the source. And I propagate, I explode, and I look at that from top down. I have 3 components, horizontal, 2 horizontals and 1 vertical, and I'm looking at the wave field. Horizontal left, horizontal right, and vertical component. The left is the real data, the right is the generated data. They're not identical because I condition it on the location of the source, and not supposed to be identical. These are generative models, they look similar, right? But the rough characteristics are the same, and I'm learning the probability distribution, which means every time I generate the same location, I have a different realization of the random field that I'm propagating through. But you can see the main features of the explosive source, and also the ripples of the propagation. And you can also see this in video. You can see the location, a condition of the location of the source, and it propagates outwards. And you can see how the model progresses. And this is clearly the same problem. And so I can sample that distribution many, many times, and I can generate the wave field and its variability with respect to the medium. The cool thing about it being a operator is that I can do super resolution. So I learned it at a resolution 32 by 32, and I can now go at a resolution 4 times higher. And it's the same problem. I can generate it at a higher resolution because I have a continuous function, right? And you can see how much more detail I can generate, even if I learned it at a lower resolution. So long as the underlying physics are the same. I cannot go to a turbulent regime if I learned it in a low Reynolds number regime, right? I mean, so long as I'm in the same physics realm. Now, last complication that arose was the fact that these are point sources in the Bay Area. The fact that our problem remained multi-scale. Not only I had to go to a higher resolution, but the higher resolution I went, the more details the wave field saw in the near surface that I had to capture with my algorithm. So we added one more step to the machine learning algorithm to learn how to translate, what features does the wave field see when it goes from, for example, the 1 hertz to the 2.5 hertz. Those really tiny details in the near surface that I can't see with the coarse resolution, and I can see, and we call it the super resolution operator. Now, the difference between that and the related operator from matching model is that this is deterministic. So my probabilistic model goes up to 1 hertz, and everything above 1 hertz is deterministic. However, I can go from a coarse model to a high resolution model, as high resolution a model as I want, once I learn the 1 hertz coarse features. I'll show you the results, but I want to show you what it is we used to learn from. So we used 2,000 simulations of point sources that Konstantinos Archidis, who works with Tema Callen, was very nice enough to run for us. These were used to train our machine learning algorithms. These were trained at 1 hertz. And then because the argument is that we can do super resolution, then we ran 40 simulations at 2.5 hertz, and these are the ones, the distribution of which we compared against our machine learning algorithm. The scale of the simulations that we ran is this. So this is the amount of data that we were able to learn. And this is not trivial. Right? That's what I'm saying. We were able to also generate machine learning algorithmic novelty. And this is the state, basically the state of the art, if you will. On the left-hand side is the simulations. The right-hand side is our machine learning. This took a second. for a point source. I don't know how much this took. Konstantinos is probably in the room, he can tell us. But this is a point source that was not in the learning database. I can put it anywhere I want to in the Bay Area, I can get a simulation. Now and the point, the filtering of the right-hand side, of the figure on the right-hand side, in the time domain should have been such that it should have cut the point source of the next simulation. Forgive the clumsiness on my end. But a point source here, the ground truth, if you will, the real data, the simulated data by LBNL is the blue. The reconstructed red is not identical because we generate new knowledge, new simulations, but it is the same, so to speak. It is the same phenomenon. It just has the probabilistic uncertainty because we learned the probability distribution and then we are sampling from it. Now, so now what? Right? You learned a bunch of point sources and you can give me a point source anywhere. I mean, that's a good, that's good progress. But to write a paper in science, which we're hoping to do, I want to be able to do this and to do it anywhere. Right? So the hope is now that we will go from point sources to finite sources using the earthquake, the rupture generator that we have been discussing all day. And the reason why I can do that, and I probably am done, right? I should be done 5 minutes ago. The reason why I can do that is because my model is probabilistic. So I can learn point sources on this, and if linearity superposition works, then I can add them one on top of the other, and I can formulate the points, the source time function at every patch according to the rupture generator, and I can learn the mapping from the source to the surface. And if I do that for point sources, I can develop it, I can stitch them up for every rupture generator output that Urban's code gives me. So long as I have somebody to give me the initial set of simulations to learn from. So under construction. And the last slide before I say you kick me out one way or another is I am not happy with stopping there because I believe that and Roberto Paluccio called me a pessimist, and maybe I am, that we will never know the shallow crust to the detail that I would like to be able to trust the high frequencies. So there needs to be a way for us to add some knowledge back inside from the observations themselves. So part of that project that we have is the attempt to try to fuse back in those machine learning models knowledge from the high frequency of observations themselves. And this algorithm is being constructed as we speak, is actually being tested, and is based on a graph neural operator. And so wherever we have observation, high frequencies will be taken from the ground truth itself, the observation itself. And wherever we don't have, we're just going to know something about it, plus uncertainty. And the more we add to the physics-based simulations, the less uncertainty we will have, because the closer we will be to the observations themselves at the locations of the strong motion stations. Okay, now I'm being kicked out physically. Products and the people who did the real work. Thank you so much.
Thank you, Domniki. So this last point you made about fusing the observation, is this like from the geotech array in SMIP or something? Or
No.
because I see you put that up.
Oh, I mean, I just pulled I wanted to pull a picture that talked about strong motion. No,
Okay.
my hope is that the strong motion station that, I don't know, the UGS strong motion, any strong motion station that we can. No noise, because I need a point source. I mean, I need sources, the earthquake sources. I mean, a strong motion station, a strong motion network. Northern California, Southern California, I mean, whatever we can. No SMIP, no, I don't, no metadata, actual time series. Oh.
Any other questions?
Arvin. Yes?
So, Domniki, this is really a very exciting
Yes.
project, although I have a feeling that it's going to put us out of business
No,
soon.
no, because what am I going to learn from? No, see, that's what
Just
I'm saying.
kidding,
It's
just
yeah,
kidding. So, yeah, so my
partially
question
out
is,
of business.
my question is, do you have an idea how many point sources are needed to train a data set that we're going to use for a magnitude 7 earthquake?
I think that I need maybe with the current set of point sources.
For 5 hertz simulations, not 1 hertz, but 5.
To go from 1 to 5, for me, is just a super resolution upscaling. I don't know.
But do you have an idea?
It's the
how
same.
many-
For the resolution for us has nothing to do with the number of simulations, because we learn that the continuous function is the same number. It doesn't affect the number on our end. It affects the amount of data we're learning, so that's why
Yeah,
we're breaking
yeah.
it down. But it doesn't affect the number of simulations. I need 1,000 to learn 1 hertz. I need 1,000 to learn 5 hertz. I learned the continuous function, so it doesn't matter. So, but I mean, we needed new technology to learn even the 1 hertz, because there was no technology out there to learn that much amount of data in that many frames. But it doesn't matter, because the resolution we're learning is continuous. But for the magnitude 7, I will learn the individual Green's function I was talking about. So I'm just going to try to teach them.
Yeah, but my question is how many we need to cover the full range of depths and, the spatial
What is the
0 to 15.
What is the 0 to 15?
So yeah, that needs to be tested. Yeah, start with a low number and then
1,000 to 2,000.
okay.
Yeah. Because the thing is, we can learn the
But
in between. We can
I
learn
still
the in
don't
between.
get one thing though.
We can learn the in between. You know what
You
I'm saying?
tested the 1 hertz simulation with a stochastic model, which has some kind of correlation length, and it worked well, but it depends on correlation length of the perturbations. But based on what you just said, I can go from, let's say, 1,000 to 100 data points. Is that going to work?
1,000 to?
Because you said if you want to go from 1 hertz to 5 hertz, 1,000 is going to work for both cases.
Yeah, well, if I have 1,000 1 hertz simulation, 1,000 5 hertz
Right,
simulations.
but my understanding is that if we go to a much lower number, let's say we cannot afford 1,000 simulations, but we can afford 200. How much do we lose in terms of modeling high frequencies?
It's not the high frequencies. We are not learning frequencies.
So you mean you
We're
cannot
learning
cover,
we're learning wave propagation frames.
so you may not cover all scenarios. That's what you mean.
It's not the same. Think about
Not
it
the
in terms
frequency
of
range, but the same.
think about it in terms of, you know how you write in ChatGPT a prompt, give me I don't know, an astronaut on a horse, and then you get a picture. Well, I need that many these pictures. So I'm learning this sequence, and so I need enough simulations to be able to learn this sequence. And if it's coarse or if it's finer, it's one thing, but I need enough simulations to be able to learn the wave propagation. I'm learning the video.
Okay.
Mm.
Well, thank
Sorry.
you, Domniki.
You're welcome.